So, have you ever wondered how you could teach a machine to win a super complex game, not by handing it a rule book, but just by letting it learn from pure experience? Well, that's the magic of reinforcement learning, and that's exactly what we're going to break down today. Here's our game plan. We'll kick things off with the why this is such a big deal. Then we'll build up the core framework piece by piece. We'll see how it all clicks together in a learning loop, check out a classic real-world example of it in action, and then wrap everything up with the key concepts you'll absolutely want to remember. All right, so first things first, why do we even need something like reinforcement learning? Well, it's because for some problems, you just can't write a step-by-step instruction manual. Life is way too messy and complicated for that. And that brings us to the central question, the big one that RL tries to answer. I mean, think about mastering a game, or even controlling a robot. You know the final goal, right? Win the game, make the coffee. But you can't possibly define the one single correct move for every single moment that could ever happen. It's impossible. So how does a machine ever figure out how to navigate all that on its own? To really get RL, you've got to see how it's different from other kinds of machine learning. So supervised learning, for example, that works with instructive feedback. It's like having a teacher with an answer key who tells you the correct answer is C. Reinforcement learning, on the other hand, uses evaluative feedback. This is more like a coach who watches your move and just says, "Nice, that was a pretty good one," but doesn't tell you if it was the absolute best move you could have made. This difference is everything. The agent learns by judging how good its own actions were, not by being told the right answer from the start. Okay, so to really dig into this learning process, we all need to be speaking the same language. So let's break down the core RL framework and get familiar with the essential lingo. Reinforcement learning isn't just some vague idea, It's a formal framework that really defines this whole interaction. And at its very heart, the entire problem is described using just three key concepts: states, actions, and rewards. First up, we have the agent. Just think of the agent as our main character. It's the AI, the program, the robot, whatever it is that's trying to learn. It's the one calling the shots. Now, the agent doesn't just exist in a void. It's interacting with its environment. This is the world the agent operates in. It could be a chessboard, a video game, maybe even the real world for a robot. The key thing is the environment is everything that's outside of the agent's direct control. So how does the agent even know what's going on? It perceives the state. A state is basically just a snapshot of the environment at one specific moment in time. For a chess-playing agent, the state would just be the exact position of all the pieces on the board right now. Okay, so based on whatever state it's in, the agent chooses an action. This is how the agent actually does something, how it influences its environment. In our chess game, an action would be moving a pawn or sliding a rook across the board. And this is the most important part of all. After taking an action, the agent gets a reward signal. This is that evaluative feedback we were talking about. And it's just a number. A positive reward is like a good job. A negative reward is like a penalty, an oof, maybe not do that again. And the agent's one single, solitary goal in its entire existence is to choose actions that get it the biggest total reward over time. This quote just perfectly captures a really subtle but vital idea. A reward is immediate. It's that instant pleasure or pain from a single action. But a value, that's about the long game. It's a far-sighted prediction. A certain move in chess might have a low immediate reward, but it could have a huge value because it sets you up for a massive win later on. It's like sacrificing a pawn. The immediate reward is negative, but if it leads to checkmate, its long-term value is massive. That's the core of strategy right there. So now that we have all the main players, the agent, the environment, and all that, let's see how they all fit together in this continuous cycle we call the agent-environment loop. This is the fundamental rhythm of reinforcement learning. It's a constant back and forth. Step 1, the agent looks at the world and sees the state. Step 2, based on what it sees, it takes an action. It makes a move. Then, steps 3 and 4 kind of happen at once. The world changes to a new state, and it gives the agent a reward. And then, the whole thing just repeats, over and over and over. And with every single loop, the agent is learning just a little bit more. So the agent is out there acting and getting rewards. But how does it actually get smarter? How does it improve? Let's dive into how an agent actually learns from this constant stream of experience. The real secret to learning is getting better at predicting the future. The agent is constantly making estimates about the long-term value of its current situation. And a really famous way it does this is called temporal difference, or TD learning. The idea is actually pretty intuitive. The agent makes a guess about how good things will be. Then it takes one step forward and sees what actually happens. It sees the immediate reward and the next situation it lands in. It learns by comparing its original guess to this new, slightly more informed reality. It's literally learning from the difference over time. Let's make this super concrete with a simple algorithm called SARSA. Here's how it works. You start in a state and you choose an action. Then you see what happens, you get a reward, and you find yourself in a new state. Now here's the cool part. From that new state, you think ahead and decide what action you would take next. You use that entire 5-part experience to go back and update your opinion about that very first move. It's basically asking, knowing what I know now, was that first move a good idea? Then you just move forward and repeat the cycle. And that's exactly why it's called SARSA. The name is literally an acronym for the sequence of things the agent uses to learn: state, action, reward, next state, and next action. It's a great way to remember exactly what information goes into that learning update. Now, this might all seem a little abstract, but these core ideas, they've led to some absolutely incredible results. So let's shift gears from theory to a really famous application. Back in the early 90s, a program called TD Gammon showed the world just how powerful this stuff is. Using that same temporal difference learning we were just talking about, it taught itself how to play backgammon, and it didn't just get good. It reached the level of the very best human world champions. It was a massive breakthrough. So how on earth did it do it? Well, the concept was shockingly simple. It just played millions and millions of games against itself. It started with zero human knowledge, no strategy guides, nothing. The only feedback it ever got was at the very end of the game. A +1 for winning, a -1 for losing. And by just constantly updating its predictions after every single move, it discovered brand new strategies, moves that even human experts had never thought of. It was powerful proof that this complex, truly intelligent behavior could just emerge from these simple rules of interaction. Okay, we have covered a ton of ground, so let's just pause and boil it all down to a final summary of the absolute key concepts you need to walk away with. Here are the essentials. The agent is the learner. It exists in an environment. It perceives the current state, takes an action, and gets a reward. And please remember, the ultimate goal isn't just about getting the biggest immediate reward. The true goal is to learn a policy, a strategy for choosing actions that maximizes the total cumulative reward over the long run. That's the key to far-sighted, intelligent behavior. And that leaves us with a final question to think about. If that reward signal is the only guidance an agent ever gets, then designing that signal is incredibly important and often really, really tricky. So think about it. If you had to teach a robot to make coffee using only reinforcement learning, what rewards would you give it and when? Would you only give it a reward for a perfect cup at the end? Or would you give it tiny rewards for each correct step along the way? The answer isn't simple, and it's one of the most fascinating challenges in actually applying RL today.